Hi everyone, my name is Jalin Hao and I want to present to you my PhD defense on the topic of static risk-sensitive reinforcement learning. My advisor is Marek Petrik, and without further ado, let's get started. So first, we will introduce the preliminaries like Markov decision process and motivation on risk measures, and then we'll talk about the prior work on risk-sensitive MDPs. Then we'll go through our research overview and each of our contributions independently. So Markov decision process is a framework that commonly used in reinforcement learning. It consists of a tuple of 5 elements: states, action, transition, reward, and discount factor. We'll use a simple grid world example to illustrate each of these components. This is a common example known as the cliff walk. And in this grid world, each of the state where the agent can be in is known as our state space. And the feasible actions left, right, up, and down is the action space. And then MDP also contains immediate reward functions that depends on the current state, the action taken, and the state that the agent ended up in. And in this simple example, the reward is merely just depends on the state that the agent ended up in. If the agent ended up in a fire pit, it get a cost of 100 and it has to start over. If it get to this resource state, then it will get a reward of 1. If it's in any other states, then it will cost 1 to operate. MDP can also handle stochastic transitions. Given a state and actions, it can have different probability to transition into different states. Last, MDP can also have discount factor. When the discount factor is less than 1, the agent will prioritize more recent reward than the later one. So in this case, the agent would prefer the right actions, which getting a reward of 1 at every single step for the next 4 steps, compared to the left actions, which get 4 reward after 4 steps. So the goal of an MDP is to find a policy that maximizes the expected total discounted reward. A policy can be seen as this illustrations above. So it's a strategy. If the agent ended up in a certain state, what action the agent would take. So the standard MDP maximizes the expected total discounted reward. You may ask what this expectation is over. Note that by following the same policy every single time, because of the dynamics and the transition is stochastic, you may not end up in the same place every single time. So a simple example is that you have 2 same policy here and you run it twice. The first time, the agent get to the resource stage very quickly and have a total cumulative reward of 51.7. But following the same exact policy, the agent took longer to the resource stage and ended up with negative 56.2 total discounted reward. So the expectations here is expectations over all the possible outcome of the policy. So in the standard MDP, there is a very popular algorithm known as the value iterations, which is a dynamic programming algorithm that solves for this optimal policy and optimal value functions. When we say optimal value functions, it's the objective of the expected cumulative reward that we're trying to maximize. So how does this dynamic program works? So let's say we're interested in a 100 horizon MDP. Instead of solving a 100 horizon MDP directly, what it say is you can solve for 1 time step MDP first. So you assume you only have 1 step left, and then you solve for a one-time step MDP. You solve for the optimal value, which can be seen as the purple number here, and the optimal policy, which is the pink directions of the one-time step MDP. Then you can use the optimal value functions of a one-time step MDP to compute the optimal solution for a two-time step MDP. And then you can use the solutions for two-time step MDP to compute for the solution of three-time step MDP and iteratively. So by building solutions of 100-time step MDP, you start to build from one-time step MDP, two-time step, three-time step, and so on, up to 100-time steps. And as a result is you have a 100-time step MDP policy, as well as the value function that tell you how good it can be if it acts optimally. And then here we show evaluations. By evaluations, we simply run 10,000 Monte Carlo simulations following the optimal policy of the standard expectations cumulative reward that we just get. So when we run the Monte Carlo simulations, we can see that on expectations, we get a total cumulative reward of 28.86, which seems to be great. But what if we want to deploy this in the space rather than our laboratory? So the deployment in the space, the robot and everything is more expensive and the cost is more expensive. But let's assume the dynamics is the same. And now instead of single unit, your unit is in millions of dollars. Okay. Instead of excited about 28.86 millions of dollars you're gonna make on average, as a product manager, you are actually afraid that 13% of the time when you deploy this policy, you're gonna lose hundred of millions of dollars. So you're wondering if there's any less risky alternative. By less risky, we mean that if there is any alternative objective that would give you distributions that allow you to lose money less likely compared to 13% of the time. In this case, it's maybe you lose money only 4% of the times rather than 13% of the times. So not only this synthetic example that we made up interested in this type of objective, actually in a lot of the domain like motion planning, autonomous system, healthcare investment, when someone's life is on stake or when there's a lot of money at stake, decision maker like manager or product manager really interested in risk averse or risk sensitive decision making. To understand what alternative objectives are there, we need to explain something called risk measures. More generally, a measure is a function that convert a distributions to a single number so we can compare them easily. And with the example before, we have two distributions. We can see that if we maximize the mean will not pick the distribution that has less risk. So we were wondering if there is any alternative measures that would prefer the less risky distributions compared to the more risky one. So next, we introduce something known as a value at risk. The alpha value at risk is the maximum alpha quantile. In here, when you're interested in 5% value at risk, for example, you get to guarantee that 95% of the distributions is going to be greater or equal to your value. If you use VAR 5% as your risk measures, then it would prefer the less risky green distributions over the more risky blue distributions. So one question the product manager has is there any disadvantage of using these risk measures? Yes, more specifically, if you use VAR, it only care about that quantile points. It doesn't care about the tail. So if you have two distributions that have same quantile points, but one have a much higher risk, at the tail compared to another, it couldn't distinguish between them. So here we need to introduce another risk measure known as CVAR. There is two ways to compute CVAR, the primal form, which is supremum, and the dual form, which is the infimum. So what CVAR trying to compute is, instead of looking at the whole distribution, it just look at the alpha tail distributions, and then it compute the average or the expected value of that tail. So in this case, you cut your distributions to just the worst 5%, and then you compute the mean based off that. So if you compare the two distributions right now with their CVAR value, the red one will be more preferable compared to the green one, and therefore CVAR is better detecting tail risk compared to VAR. And there is another question. Okay, CVAR is great, but are there any drawbacks with CVAR? Yes. More specifically, is VAR and CVAR, they solely focus on the tail points and the left tail distributions. But what if you have two distributions that have similar left tails but different upsides? The teal distributions, although having similar tails, but it has a higher mean compared to a red distributions. In this case, VAR and CVAR cannot distinguish between which of these distributions is better, but EVAR could. EVAR of 5% in this case would prefer the teal distributions compared to the red distributions. So before we explain EVAR, we have to explain something called entropic risk measure, ERM. What ERM uses is something called the exponential utility functions. So what this function does is, if you have a bad outcome, the utility of the marginal decrease, it make it exponentially worse. Okay. And if you have a good outcome, the utility of that good outcome decay exponentially. As a result, bad outcome looks much worse. Good outcome seems to be not that good. One concern about ERM is this exponential coefficient beta that is hard to choose. We know that when beta is 0, you get expected value. When beta is infinity, you get minimum. But how do you choose the right beta? So what EVAR does is, given an alpha, this is the quantile value, EVAR uses ERM. It helps you find the appropriate beta such that you get the tightest Chernoff lower bound for your VAR of alpha quantile. Okay. And EVAR can also be represented in two forms. One is the primal with the supremum, and another one is a dual with the infimum. Furthermore, note that EVAR is always a lower bound to CVAR and VAR, makes EVAR very sensitive to risk. Not only it's sensitive to risk, it can also reflect to the value above the tail distribution. So despite it's always lower than CVAR and VAR, when you have a distribution that have the same tail but different upside, you can use EVAR to distinguish which distribution is better. So all in all, a risk-sensitive MDP trying to optimize an objective that maximize the risk of the total discounted reward. So here we have a summary table on each of the interpretation of their risk level and what part of the distribution they consider and how sensitive they are to risk. But more specifically, let's focus on the time consistency and positive homogeneity property. Note that expected value have both of this property, but none of the risk measure has both of these properties, which means extension it with the value iterations of value, it's not that straightforward to these risk measures, and we will explain it in the next chapter. So prior work and overview of MDPs and risk-sensitive MDPs. Remember, we mentioned the standard MDPs that solve a risk-neutral objective that maximize the expected cumulative reward can be solved with a value iteration shown as below. The reason why this is true is when you expand the value iterations, these two equations hold with equalities. So what this means is you can write your optimizations of mean in terms of optimizations of conditional mean with one time step less. So you can write VT in terms of VT minus 1. However, if you just change your objective to any of these risk measures and change the value iterations risk measures to the 1, this two equation doesn't hold with equality. You can still solve this dynamic program, but it is not what you're trying to optimize for. So this dynamic program is known as the nested risk. If you're optimizing for CVAR in this dynamic program, you call it nested CVAR. If you're optimizing VAR, you call it nested VAR. So the reason that this is not equivalent is when you extend the value iterations or dynamic program, the first equation on the top is not equivalent with the bottom equation. But all in all, if you could write the optimizations of risk in terms of optimizations of conditional risk with one time step less, you can derive the dynamic program. It's just the naive way of just changing these risk measures. It's not the right way to do it. So although we know it's not the right way, a lot of work trying to solve this because it's easier, it get a dynamic program. So the algorithm is known as the nested CVAR. Here we illustrate a simple example on showing that how bad the nested CVAR could be, approximating the true CVAR. We use 5 time step, where each time step you get a standard normal distributed reward functions. And you can see that the nested CVAR is a very poor approximation to the true CVAR. And generally, if you approximate CVAR with EVAR, you get a better approximations. So now we talk about how you cannot use nested risk measures to optimize for the risk-sensitive MDP objectives. And a lot of this work trying to solve the static risk-sensitive objective by trying to figure out what's the correct dynamic program you should be solving. So current decade, this dual methods has been really popular. And we were trying to analyze and understand and fill in the missing proof in these dual methods. Unfortunately, while we're trying to fill in the missing proof, we realized that a lot of this algorithm, it's not accurate. Instead of proving that they are right, we accidentally prove them they are not correct. However, although it doesn't work for CVAR and EVAR, we show that this algorithm could work for VAR. Moreover, since we disprove all the dual methods for CVAR and EVAR, we realized that there is no algorithm that solves EVAR MDP. So we propose a EVAR MDP algorithm that is based on the primal representations of EVAR. And this algorithm is delta optimal. Given any delta that you can tolerate, it gives you a polynomial time algorithm that guarantee that you are less than delta away from the true optimal solutions. Moreover, we also noticed that the CVAR and VAR dynamic program is not practical because it has this real number state space, which is not practical to solve. So we propose a practical algorithm to solve VAR MDP, and that algorithm can also be used for CVAR MDPs. So without further ado, let's get started into our first contribution step, proving the DP decompositions for coherent risk measure doesn't work for optimizations, which we disprove a lot of this paper. What happened is this idea is actually introduced in 2012 by Fluck and Feature, saying that you can write a coherent risk measure into the conditional form of coherent risk measures. Also note that for simplicity, instead of total cumulative reward with t time step, we simplify it with 1 time step MDP, where the current states and the next states are both random variable. And then when you look at the conditional form, the current state is no longer a random variable. So the above one is just trying to decompose the risk measure. But in MDP, instead of just decomposing the risk measures, you're trying to find out the optimal policy that maximizes the risk measures. So you have this maximize pi here. And throughout the decade, people has thought that you could do this correctly. This is a correct representation of the dynamic program. But we show this is not quite true. More specifically, this equality does not hold. So it's okay you use it for evaluations, but when you're trying to do it for policy optimizations, and there is a problem. More specifically, what happened is there is a missing steps here. So there is a duality gap, which has an inequality. As a result, if you compute the dynamic program based on a lot of this algorithm, you would be over approximating your true objective. Okay, let's analyze this function, the max pi min zeta and the min zeta max pi. So the min zeta for each of the policy. So we have a two policy here, the blue and the red. So the min zeta of the blue policy is this pentagon here, and the min zeta of the red policy is this golden pentagon here. And the maximum of both of them is the golden pentagon, which is the left-hand side. Furthermore, for each of the zeta, the maximum over theta is this dotted line. And the minimum over the dotted line is this purple square. So what this say is that the purple square is greater than the golden pentagon. But what does it even mean? It means that when you're trying to deploy this dynamic program, you will get over approximations on how well you do. Moreover, the policy you get here may not be the same optimal policy you get from your objectives. So when you follow the policy you think is good, the performance of your policy is actually way worse than what you think. Not only CVAR has this problem, we also evaluated EVAR as well. First, we propose a EVAR decomposition for evaluations, which means you can write EVAR in terms of conditional EVAR in this form. However, same problem exists when you're trying to do it for policy optimizations, and EVAR fails with the same exact reason that CVAR fails. Next, we're going to talk about var. More specifically, var, you can write var in terms of conditional form of var. You can also write the optimizations of var in terms of optimizations of the conditional form of var. So one question may be interesting is how is this different from CVAR and EVAR? More specifically, if you look at the zeta and the pi, they are optimizing in the same direction. They are looking for the supremum and the maximum in the var. But for CVAR, they are looking at min max. So in the CVAR, you have duality gap. But if you're optimizing for the same directions, swapping them would not give you any inequalities. Moreover, you still have to swap a min-max in var. But this time it's okay because swapping the min state and max policy, it satisfies something known as an interchangeable property by Shapiro in 2012. Shapiro has proved that swapping this is okay. So as a result, you can write your optimizations of var in terms of optimizations of conditional var. And because of this, we mentioned that if you can do this, you can have a dynamic program. So for any t time step MDP, you can derive the dynamic program for your var MDP objectives. However, one thing that is problematic with this dynamic program is that you have an alpha between 0 and 1, and in this interval, there's infinitely many numbers, and it is unclear how you could solve all the numbers in between these intervals and how you would discretize it if you don't want to solve every number, but still give you the same guarantees. We'll talk about it later, but now let's talk about EVAR MDP because we don't have a good algorithm to solve it. So now we propose an algorithm to solve EVAR MDP. So first, we're going to solve ERM MDPs by recognizing that EVAR MDP can return as ERM MDPs. We will solve EVAR MDPs later. So high level, ERM MDPs cannot use the standard value iteration as well. And the problems lies in the fact that you can't move the discount factor in and out of the ERM at will. And this is what causes the inequality. So after we find the root cause, we also have a new insight that although ERM is not positively homogeneous, which means you cannot move this discount factor in or out at will, it is something called quasi-homogeneous, which means you can still move it out, but you have to change the risk level. So we propose a dynamic program with this new insight that is time dependent. So which means that at every single time you have to update your risk level based on the time steps of your MDP. And this concludes the ERM MDPs. Next, we're going to go to EVAR MDP. So let's write the total cumulative reward as capital R of T. And what this EVAR MDP representation say is instead of EVAR MDP, you can actually solve a bunch of ERM MDP and compute the supremum over these MDPs. However, there's infinitely many number beta greater than 0, so it's not clear how you compute this supremum. So we analyze this function and call it a h of b. Note that when we analyze this function h of b, we can see that this EVAR functions is concave, quasi-concave with respect to beta for a fixed policy. But there is a maximum pi here. We're trying to find the optimal policy. When there is policy optimizations, this function is no longer concave. So we cannot use gradient ascent or BFGS to get us the policy. So next, what we propose is, instead of looking at all the real number greater than 0, we propose that if you give us a delta, which is your tolerable error, we could construct you a set B with this beta inside it. And if you just compute the max over this set B, you get to guarantee that your solution is less than delta away from the true optimal solutions. So now you don't have to solve for infinitely many betas. You can just solve for beta in the set B. And the magnitude of this set B is quadratic with respect to delta. Delta is your error. So for delta 0.1, it actually have to solve only 8 points. And what we say is that by solving only 8 points and you compute the maximum of them, you were less than delta away from the true maximum of these functions. As a result, EVAR MDP algorithm is very straightforward. First, given a tolerable error, you try to compute the discretization B. Then for each beta in B, you compute your MDP and then add the penalty functions and trying to find which one is the maximizer. And you use the value functions and the policy of the maximizer. Next, let's see how EVAR MDP would behave. One very interesting thing is that in EVAR MDP, the agent very averse to risk and would choose to face the wall in the starting state and hope that 10% of the time, due to stochasticity, it go to the right state. And as a result, none of the agent actually fallen into the fire pit at all. And when we evaluate the performance of the EVAR MDP across different risk level and over the risk measure EVAR and CVAR, we can see that it performed well generally. But before we do that, let's talk about each of these benchmark algorithm we compare with. E referred to the standard MDEP algorithm that optimized for the expected cumulative reward. VAR and CVAR is based on the dynamic program we introduced earlier for VAR MDP, and CVAR based on Borlase and Ott algorithm. And these two algorithm has a continuous state space, so we propose a discretization scheme in the next chapter that would explain how you would construct a policy optimize this VAR and CVAR MDP. Next, EVAR. This is our EVAR algorithm that guarantee delta optimally in polynomial time. And we have this NVAR and CVAR and EVAR, which is the nested algorithm that based on the standard value iterations, but replacing mean with VAR, CVAR, and EVAR. Last, we have Chow here. Chow is the algorithm that uses the dual decompositions of CVAR in policy optimizations. And when we compare all these algorithms, we can see that if we are interested in the EVAR objective, our EVAR algorithm consistently perform the best among all algorithms. And even if we interested in CVAR objective, we can see that this EVAR algorithm also perform consistently well because EVAR is a good approximation of CVAR. So next, we're gonna talk about that the VAR dynamic program is continuous. So how you could make a practical algorithm that still gives you guarantees. And our algorithm can be used in CVAR as well. More specifically, we have seen VAR MDP and the dynamic program for VAR MDP. but we talk about the problem is that the state space is continuous and is not practical to solve for all the alpha in between 0 and 1. And what can you do? What we propose is that you can use discretizations that always over approximating or always under approximating your true value functions. If you follow the DP that use the value function that always underestimating your true value functions, by following the policy of your over underestimate value functions, you get to guarantee you perform better than that because that is under approximating how well it does. Moreover, if you keep over approximating how well you can do, then this over approximations is an over approximations of the true optimal policy. Note that both your policy and the true optimal policy is in between these two lower and upper bound. Next, we're going to show with different number of discretizations how this bound change and how this yellow region change. So we have 3 examples with 3 different discretizations. Note that the policy performance of our lower approximation value functions is always guaranteed to be in between these 2 upper and lower bound. The true optimal policy is also guaranteed to be in between these 2 bounds. As we increase the discretizations, these 2 bounds shrink and get closer and closer to each other. And eventually they overlaps. When they overlap, you get to guarantee that the performance of your policy is optimal. So here we kind of demonstrate the VAR MDP policy execution. Note that in some of the states, the agent have different actions. This is because the optimal VAR MDP policy is history dependent. What the agent does actually depends on where they have been in the past. Furthermore, you see some of the agents just trying to face the wall, not doing anything meaningful. And this is because we mentioned earlier, VAR only care about the quantile points. Anything below the alpha quantile will be ignored by this risk measure. So no matter how good or how bad it does, if the agent know that it can never go above the quantile value, then it will just give up and doing random things. So as a result of our algorithm, if we evaluate the VAR performance of each of the algorithms, we can see that our VAR algorithm perform best consistently across all the others risk levels as well as algorithms. Note that this discretization scheme can also be used for CVAR, which has the same problem that has a continuous parameter. And if you follow the lower approximation value functions, you get to guarantee you are bounded between the lower value functions and the upper value functions. And by using the same insights, we were able to come up with a practical CVAR algorithm. Now we explain how you discretize, and there is another problem in VAR is how you solve this in a model-free environment. So more specifically, in the model-free environment, you don't have access to the transition model and the reward functions, and you just have an agent and a simulations. You want the agent learn by itself. So we explain how a standard MDP consists of these 5 elements, and we call the transition and the reward functions a model. And what if you don't have access to these 2 things? How can you let your agent learn? How do your agent learn to optimize the things that you want. So one thing is letting the agent interact with the environment, and there's two methods that you can use. One is the model-based method, where you know you are missing the immediate reward and the transition probability. When you interact with the environment, you try to learn these two components, and then you have some estimates of these two components, which you will be using it to solve your risk-sensitive MDPs. And there is another method called the model-free methods. The model-free methods say that you are interested in figuring out what action is best given a state. Instead of learning the reward and the transition model, you're just trying to learn which action is the best. So let's talk about why this model-free methods is hard for VAR MDP. More specifically, VAR MDP have this dynamic program, but instead of trying to figure out what state is the best, you're trying to figure out what action is the best given the state. So instead of state value function, you have state action pair value functions. So you're trying to learn these Q value functions. And how do you normally learn it in a model-free setting is you try to find a convex loss function such that the minimizer reflect to the objective or reflect to the dynamic program you're trying to solve. What this means is if you can find the loss functions such that the minimizer of your loss functions give you the equations below your dynamic program, then you can do gradient descent, or more specifically, stochastic gradient descent. By stochastic gradient descent, you can update your estimates every single time, and eventually it will converge to this minimum, which help you solve this dynamic program without actually computing it. So how do other risk-sensitive MDPs solve it? Is all the other MDP actually relies on mean and ERM in their dynamic program. And therefore, since mean and ERM has explicit loss functions, means is the quadratic and ERM is this exponential functions, you can use this convex loss functions to solve for your model-free Q value. But what happened is in VAR, you have these constraint optimizations, which it is unclear what the optimal convex loss function is with respect to your dynamic program. However, we prove a new dynamic program that is equivalent to the above, but it's more interpretable and it's easier to find the loss functions. More specifically, this new dynamic program says you don't have to solve these constraint optimizations. All you need to do is solve a VAR that is jointly distributed for next states and a uniform distributions, and you will get the same solutions as the constraint optimizations above. And this is very helpful because if you have absolutely continuous distributions, then you can optimize for these loss functions here. This is also known as the quantile loss functions. So we'll use an example to illustrate Q learning. More specifically, for each of the states, when the agent is inside, it will be highlighted blue, and you will have 4 lines indicating each actions. And when the agent take an action given a state, then it will update that value function. So the agent just took the left, so the left value functions will get updated based on the gradient of the loss function. This algorithm is also known as a Q learning algorithm. So here we can see that whenever the agents take an action in a state, it will update the Q value functions. As the agents seen a state action pair much enough times, then it will have a more accurate value functions estimates. Instead of seeing how the value function change at every single steps, we'll speed it up to run it for every 10 iteration. We'll see how the value function change every 10 iterations. So here you can see that the value function was changing by a lot in the beginning, and then it started to converge, and then it just barely changing after a couple thousand steps. More specifically, when we compare the value functions of the Q-learning and the dynamic program, so dynamic program assume you have the model, and Q-learning assume you don't have the model. So if you have the model, then you can compute this Q value functions precisely with your var DP. And then this Q-learning would just estimate the value functions every single time when it see a sample, it will update it. And then you can see after about 10,000 iterations, the Q-learning value functions and the dynamic value functions were very identical, where on the y-axis represents the distance or the absolute error between the two Q value functions. The DP value functions is a true one, and the Q-learning is an approximations. So when the error is close to zero, which means your approximations get very close to the true value functions. So what this section says is, first, we propose a discretization scheme that gives you upper and lower bound guarantees on your var. And then we also propose a new dynamic program that is more interpretable and easier to compute. Next, we propose a var Q-learning algorithm. And this is saying, even if you don't have the model, if you just put the agents in the environment and let it try out, it will eventually learn what's the best actions to take. This concludes our practical var MDP contributions. So now, not only that a person can optimize for the mean in a MDP, they can also optimize for the var 5%. In this case, if you optimize for 5% var, you get to guarantee that 95% of the distributions is higher than 12.8. You can also optimize for 1% var, which guarantee that 99% of the distributions is above negative 9.4. You can also optimize for EVAR of 5%. And in EVAR of 5%, we saw that none of the agent actually dropped into the fire pit, which is a very risk-averse decisions. All in all, as a product manager, you can have less risky alternative to optimize for compared to the standard mean. And this concludes our PhD defense presentation. Thank you.